Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibration, continuing from the introductory part of the response to periodic excitation we discussed last. Today we are going to take this response evaluation to its finer detail, starting from taking a small example of how typical periodic excitation can be represented as sum of multiple harmonic time functions, and individually calculating the response and then summing up those responses to get the total response to a periodic excitation. Okay, so as I mentioned once, if I somehow get the decomposition done, I will individually evaluate the responses to individual harmonic time function and then add them up. So, this particular slide gives you a pictorial depiction of how that activity is done, right. So, how do I evaluate the response? For the sake of simplicity, I am now going to assume that a vibratory system is subjected to a forcing function which is periodic, the way it is shown here. This is the amplitude of the excitation function f of t. Now, that f of t comprises of two functions. Okay. So, instead of showing you the function is already shown. So, you assume that using Fourier series decomposition, you have been able to decompose that and express that as not an infinite sum of sinusoids, but just the two components of it. So, imagine that if it is an ICE engine, it is primary unbalanced force and secondary unbalanced force, you know that, you remember that. So, the secondary unbalanced force has an amplitude which is fraction of the primary one. So, if you assume unit primary unbalanced force value, then you know that me omega square cos 2 pi f t. Now, in this case omega t is being written as 2 pi f t, just for the sake of illustration. Plus the amplitude of the secondary unbalanced force times the cosine function representing the frequency of the secondary unbalanced force. So, this is just like a periodic forcing function. It would, if I use these amplitude values and these frequency values. So, please make a note here that I am using the fundamental frequency or a period of repetition to be 20 hertz. You can find that out, 0.05 time period turns out to be 20 hertz. Okay. Now, what is our usual process is to decompose the periodic forcing function into component harmonics. If I do that, let us assume that this is one component, this is another component. Once I know that, I can represent these components like this. So, the first component obviously will be having the same frequency as the fundamental frequency, which is 20 hertz, the period of repetition omega naught. So, it would look like this. Please recall that this amplitude was assumed to be 1. So, therefore, the first component of the forcing function has unit amplitude here, and it has a frequency which is omega naught, which is 20 hertz. So, if you consider the sawtooth profile, the fundamental frequency is going to correspond to this period of repetition of the original periodic time function. So, if this was 0.05, then omega naught is going to be 2 pi over 0.05 in radians per second. So, if you want to find out for in terms of hertz, which is used here, this is going to be 20 hertz. Okay. And what is going to be the second component? Second component, as we have assumed that it is having an amplitude of 0.33, right, and the frequency will be twice. because if the first frequency is omega naught, the second time function is going to have some other amplitude, but the frequency is going to be 2 omega naught. They are integer multiples. And so, if you have a frequency which is twice of the first frequency in the same time period that I am plotting this variation, you expect double the number of cycles getting completed in the same period of time. That is what is happening, just have a look at it, right. It finishes 2 cycles here, it finishes 4 cycles there, because the frequency here is twice of the fundamental, right. Am I clear? Okay. Now, what do? You have only done the preliminary basic thing, in the sense that you have identified what are the harmonic time functions of the force. Okay. And once we decide and once we assume that I can individually calculate the response of each of these components, right, and finally add the two, I get the total response. So, what is the way of finding out the response? You know the response is what? This is what we learned for a simple vibratory system with a harmonic excitation case. F naught is the amplitude of the harmonic excitation, right. So, which means that if I treat this except the F naught, this becomes my frequency response function. That is the function with to which I multiply with this force to get the amplitude. Okay. Now, obviously, x of instead of x of t, I can say that I want amplitude of the response, capital X, will be equal to this frequency response function multiplied by the amplitude of the force, isn't it? That is what I do. I multiply the system frequency response function and multiply. So, input is f, I multiply it with this system frequency response function to get the response amplitude, okay. And that because it is going, I know that what is the this force is corresponding to omega 1 or f1 frequency, isn't it. So, once I know the frequency, I can generate x of t, right. I can generate the time function here. So, in nutshell, what I am basically trying to do is, once I separate out the two harmonic components, two in this particular case, but in reality in some other time function there will be multiple of them, and just for the sake of illustration we have two components, and then when I multiply this same systems FRF with the input forcing function, I get the corresponding response, and I have another harmonic time function of the force, I multiply it with this to get the response, corresponding response to this particular excitation function. And what do you do at the end? Simply add them up in time, you know. So, I add this value at this time and at the same time this value to generate at the same time this particular value. So, I simply add them up in time, appropriately ensuring that they are synchronized in terms of its phase, okay. And once I do that, I get the total response of the vibratory system to a periodic excitation function, provided our system is linear, okay. Most of the times that assumption is more or less valid, okay. And in most of the times, even if it is not strictly linear, the response obtained is reasonably accurate. We want reasonably accurate result, okay. All right. So, this is the complete response. Now, wherever the amplitudes become larger because the forces are too large, okay, then our force and displacement, or force and the corresponding deflection, that relationship is no more linear. The interesting example is of bearings, a ball bearing. Now, you apply the force, the stiffness is strictly not linear, even with a lower value of load. Okay. The stiffness continuously changes as you keep on increasing the force. Okay. So, if the shaft deflection is not significant, which is what the case with all the stubbier and thicker shafts or shafts with larger diameter, then the bearings compliance or bearing stiffness plays a dominant role in that case. Then the system is really non-linear one. Okay. Then in that case, the response that you will get by actual measurements will not be only a harmonic one, even if there was only unbalance as an excitation. Yeah. So, all of those support structures where the coefficients or the parameters of our vibratory system, be it stiffness, be it damping, if they provide this kind of relationship, you will get a non-linear response. The system will be that way linear. Okay. But then why are we always using this linear assumption? It is very important to understand that as well. So, the question that has been posed is that what is the example of a non-linear system? So, I gave you the example that the rotating shafts supported on rolling element bearings is strictly a non-linear system in because of the way bearings offer their stiffnesses. Now, unless you understand this linear vibration response, you may not be able to appreciate and understand and in fact evaluate later and comprehend and infer from the response that you will actually eventually observe for a nonlinear system. When you actually start looking at nonlinearities and nonlinear vibrations, unless you have this foundation of linear vibration response strong and clear, it will be difficult for you to realize and understand the nonlinear vibration response. That is why we have to understand first the linear one and then start looking at what if the system has nonlinearities. Okay. Then you will be able to better appreciate what you are observing, what you are getting mathematically also. Okay. That is one aspect. The second aspect is, for most cases you do get the amplitudes are small enough, you do get linear vibration response and so on. Okay. So, the second reason for that is this. And now you are clear. See, had you jumped directly on a periodic excitation case, would you have understood what we are talking about? No, because at the back of your mind you have already learned the response to a harmonic excitation. You are now in a better position to quickly grasp and understand the response to periodic excitation. Okay. We have discussed that in the first case where the period of repetition, the fundamental period corresponds to 20 hertz rotational frequency of the rotating shaft, where the unbalanced primary and secondary had these components. So, this frequency is 20 hertz, and then this, based on the system's properties, we got these two responses, right. So, what you notice here is the amplitude of the first component of the response maybe is 1.3 or so, and this amplitude is 0.5. So, when they add up, you can see that 1.7 or 8 is the total amplitude here. Okay. And then if you find out peak to peak, maybe close to 3 unit of response, right. So, 3 units of peak to peak amplitude is what you get finally for a given forcing function, which is periodic, and that happens when your rotational speed is 20 hertz. and obviously because I mean that also implies that your primary unbalanced force is having a frequency of 20 hertz. Now, let us look at what happens if I now have a situation here where I increase the speed and now the new fundamental period is slightly reduced and therefore, the fundamental frequency has slightly increased. So, instead of 20 hertz, the primary unbalanced force is fluctuating with a frequency of let us say 24.5. Okay. Now, here there is some assumption related to the damping value that I have taken, but that may not significantly alter the core result here, right. So, for a given system having certain value of k, m and c, let us say now the force is now varying with a frequency of 24.5 as a fundamental frequency. So, if I do the same process on this forcing function, the only thing that is changing is now this f is going to be increased from 20 hertz to 24.5 hertz. Now, when I do that, I follow the same process of decomposing the periodic input function forcing function into its component harmonics, and then using the system transfer function or a frequency response function to evaluate the individual responses. Individual, I mean the response here is obtained by assuming only this harmonic time function, excitation time function, and this is what I get the response, and then I individually find out the response only due to this forcing function. Okay. So, these amplitudes are now quite different. So, this one instead of 0.3 or so whatever is now shooting up to let us say 1.3 or so. This was I guess was I think about 1 or so, and now it has shot up to maybe about 8 or so, right. And then when you want to find out the total vibration response, you simply add them algebraically, right, and when you add them up, you can see what is the complete response. The peak to peak value, if you see roughly, is going to be close to 17 or 17 and a half, right, peak to peak value, sorry 17 point let us say 5 peak to peak value. What was the value in the previous case when the speed was 20 hertz? Was I think about 1.3 or so, is not it? It has shot up to this value. Now, we are going to understand a very important implication of analyzing the response to periodic forcing function. Now, why is this happening? In the first case where the operational speed was 20 hertz, the first harmonic of the constituent forcing function harmonic was having a frequency of 20 hertz. Its second harmonic, when I say second harmonic means is the second multiple, 2 times the fundamental frequency, was having an amplitude of so much and a frequency of so much, right. So, these are the 2 component harmonics of the original forcing function. It had a fundamental period which translates to a frequency of 20 hertz. Now, the system that I chose for this sample evaluation is having a natural frequency of 50 hertz. Clear? Now, what is our basic premise? That you should not operate at a speed which is close to the natural frequency, right. What was the speed of speed of rotation in the second case? Of course, in the first case it is 20 hertz, far away from your natural frequency 50 hertz. What is the rotational speed in this particular case? 24.5 hertz, far away from 50 hertz natural frequency, right. But we have a problem here that even if your rotational speed is 24.5 hertz, far away from natural frequency of 50 hertz, your second harmonic of the forcing function, one of the components of the forcing function, is close to the natural frequency omega n. Okay. So, even if omega naught or omega naught is far away from omega n, and we believe that there is no resonance, but the second harmonic of the forcing function is very close to the natural frequency, and that is actually causing a resonance, right. For a resonance to happen, it does not matter how much is the force amplitude, right. So, even if this particular component has lower amplitude, 1/3 of the main frequency or the first frequency, it still can generate resonance. You require matching of the frequencies, right, when you call resonance. So, if I now look at this frequency response function or a dynamic magnifier, earlier I was operating somewhere here, and now I am operating almost here, very close to the natural frequency. I am sorry. So, earlier I was operating maybe here, and now I am operating here, but then the second harmonic was somewhere there, which is still far off from the natural frequency. But now when I operate with my operating speed to be away from the natural frequency, the second harmonic has now started becoming close to the natural frequency, and that has amplified the component of the response corresponding to 49 hertz, while the amplification of this particular frequency component 24.5, that amplification is still not much, okay, but this amplification has been quite substantial, and that is the reason that in this particular case the peak to peak amplitude was 1.3 units, and this went almost close to 18 units. All right. So, this brings us to a very important issue, is that when you want to analyze a given mechanical vibratory system for its vibration behavior and response, it is not only important for you to understand your parameters of the vibratory system like estimation of K, M and C, but it is also equally important to assess and understand what your forcing function is going to look like. And you need to know what is your exact forcing function and what are the components of it, and then make sure that you not only focus on your operating speed, but also look at all other frequency components, and the way you need to keep this one away from the natural frequency, you also need to keep this one and subsequent ones away from the natural frequency. Okay. A small but important passing remark here is that all of this is your system's property. So, the amplitude here x, even close to resonance, is going to get amplified because of this, okay, right, but the absolute amplitude value actually is going to be multiplied by the amplitude of the force. Okay. So, there would be amplification, there would be resonance, but the strength of that resonance is going to be smaller. Now, you may actually calculate this response by operating this not at 24.5, but at maybe 48 or 49. You will find that this 18 will shoot up to maybe 100 or so, right, because your fundamental forcing function, which is having a strong amplitude, is directly close to the natural frequency, right. So, then this 18 will get further amplified, right. So, yes, it is important that you should keep all these frequencies away from the natural frequency, but mind you that the strength of the resonance, because of the higher harmonics, if they are small compared to the fundamental, will not be very strong resonance that you will observe there. Okay. So, this aspect also must be understood, and we will revisit that part in the future discussion. Is this clear now? How do we find the response to periodic excitation by first decomposing the periodic excitation function into its component harmonics using Fourier series, and then individually finding out the response of the system to individual forcing functions or the component harmonics, and then adding all the responses to generate the total vibration response. And the way this has shown that the final output vibration response is still going to have the fundamental period the same as the fundamental period of the forcing function. That is not going to change, of course. Okay. But the shape of this response is not going to be harmonic, the way it is shown here, it is a periodic one, this is also a periodic one. The shape of it might change. For example, when you are operating at some other speed, as you see here, the shape has significantly changed. Why? Because the amplitude to this forcing function and the amplitude to this forcing function will be varying in their amplitudes, and with that kind of a variation in the amplitude, the shape of this and the shape of the previous case could be slightly different, although the period will be the same. Okay, now let us take a small example which will illustrate the Fourier coefficients and how they are to be calculated, and how a periodic excitation in the form that is shown here in this example is addressed, right. So, the question here is that, as we discussed, there would be a turbine wheel with blades on it on the circumference, and they are rotating, and then as it comes to face a nozzle through which the fluid is moving in, each blade as a vibratory system is going to get subjected to a series of such step kind of forces. Now, the actual profile might slightly differ, but then this is for only illustration purpose that we are trying to figure it out as to if the forces look really as you see here in the form of short impulses, then how do I find the response, okay, or how do I basically characterize the excitation, right. Now, you would wonder that we have seen the response to a vibratory system to an excitation which was quite similar when we dealt with transient or an arbitrary excitation, did not we. Then the question here would be that why can't I use a convolution integral or a Duhamel's integral for finding out the response. That also is theoretically a correct way of doing it, but then in case of an arbitrary or transient excitation, the excitation ends shortly, it is not sustained one, but here you are going to have a continuous excitation through the series of impulses, and then it makes sense to use a method which is designed to designed to address the consistent or a sustained excitation function rather than an excitation which exists only for a shorter period of time, right. So, whenever there are transient excitation which is there for a short period of time and then there is no excitation, for such kind of a situation, yes, Duhamel's integral or convolution integral approach works well. It is not that mathematically you can still use it here, but then it will be cumbersome to use, and therefore, more appropriate way is to decompose this periodic excitation into series of harmonic time functions and then use them in the solution process. So, that is what we are going to look at, and then so it says that you may have these kind of blades which will get subjected to this kind of an excitation, and then there are, of course, as you see, there are 3 nozzles, nozzle 1, nozzle 2 and nozzle 3, through which these excitation will be acting, and it is clear that the nozzles are symmetrically placed, and then all the details of where exactly the nozzle opening starts, at what time, for which duration, everything is given, and then what is obviously clear that this is one revolution of time. Okay. So, this is time period associated with one rotation of the shaft. Okay. So, obviously in one rotation there will be 3 successive excitations as you see here. Now, there are 2 conditions for which we have to analyze the excitation function, and that is when the nozzles are symmetrically placed as you see here, and then the third case, it is not a hypothetical case that the third nozzle is removed and the stationary guide vane has now only 2 nozzles. So, supposing this nozzle is removed. Now, you would wonder how do I remove this kind of a nozzle in practical situation, but it does happen many times that when the load drops and then you want to regulate the fluid flowing in, many times like in steam turbines they close part of the steam entry and then therefore, there is a partial admission of the fluid, right. So, then it is not like removing it, it is just that the excitation is no more there, right. So, then you will not have this excitation, that excitation is missing. Then would it cause any change? That is the question, right, and we will have to figure this out in the second part. Let us focus on the first case when the nozzles are all acting and the fluid is flowing in and the blades are subjected to such excitation. Now, we all know that the excitation function defined like this will be represented by a Fourier series. We have discussed this earlier, that this Fourier series will be looking like this, and the coefficients of the series, the coefficients of individual harmonic functions, they will be obtained mathematically and the expressions are already discussed. The fundamental frequency omega, or sometimes we put a subscript of omega naught, which is the base frequency or the fundamental frequency, and then as n changes from 1 to infinity, you have just multiples of the fundamental frequency, which we call as harmonics of the fundamental frequency. Now, first thing is, what is the value or what is the numeric value of this omega naught? We already have seen that this omega naught is nothing but 2 pi over capital T, is not it, where T is the, what is T? T is the time period of repetation. Please note, in case of rotating system it need not be one rotation, it need not be one rotation, right, which is very clear in this case. Will you call this as the time period? Is this the fundamental period? It is not actually. Although this pertains to one revolution, it is actually this that is the time period of repetition. Why? Because you can see that this is the pulse which is repeating, you can notice that this is going to repeat like this. So, there will be 3 repetitions in one rotation. Okay. So, time period of repetition need not be a rotational speed in this case, or the time associated with one rotation or time for one rotation is not the time period in this particular case. Okay. So, you have to see how your excitation function in time domain is looking like, and then of course, this capital T is going to be 1/3 of the total time for one rotation. Okay. So, that is your capital T in this particular case, and therefore, omega naught will be accordingly adjusted. So, that this T is 1/3 of the time for one rotation. Okay, that is important. So, once we do all that, this capital T then turns out to be 1/3 of the time for one rotation. Now, if it is to be noted that this is RPS, okay, that is rotation per second instead of RPM. Okay, if you denote n for RPM, then it is going to be n by 60. So, that is rho in this particular case. Okay. And that rotation per second of course is the what do you call that? Hertz. It's the yeah. So, the alternate unit there will be hertz. So, we all know that time and the frequency, if frequency is in cycles per second, is denoted or they are related like this. So, therefore, the period of repetition will be 1/3 of time for one rotation. Now, time for one rotation is going to be 1 by rho, and therefore, the time, so this time is for one rotation, and therefore, time of repetition for this excitation function being 1/3 of the total time for one cycle, it is going to be 1/3 rho. Okay. Okay. Now, in the example it is given, if it is not very explicit, let me say that this time period will be based on the angular position of the nozzle. Okay. So, if it is rotating like this or if it is rotating like this, the position where this excitation function starts is obviously going to be the time it takes for moving from 0 time position to the starting of the nozzle, right. And this width will be 1/12 of a revolution, right. So, the angle pertaining to this opening would be 1/12 of a revolution, which means 30 degrees of rotation. Okay. And this one I guess is going to be 45 degrees, and so accordingly we need to calculate what is this time T1 and T2, and they will be required later on in the calculation of these coefficients A n and B n. So, what we do is, based on this information that the position of the opening of or the start of the nozzle area is 45 degrees starting from the horizontal, that is the time, I mean that is the location from where we count the time, that T1 which is the time it takes to reach the opening of the nozzle for the blade, is going to be 45 degrees. So, obviously, it is going to be 45 over 360 degrees times rho. So, this is the time which you can calculate based on the geometry and the position of the nozzle. So, this is the time T1 that you can find out, is not it. So, if time for one rotation is 1 over rho, okay, time for one full rotation is 1 over rho, then the time for an fraction of the rotation, that is 45 degrees, will be 45 by 360 times the time for one rotation, which is 1 over rho, and that is how T1 is getting calculated here. Now, the nozzle area, this angle is corresponding to 1/12 of the revolution. So, that is going to be 30 degrees. So, T2 is going to be 30 plus 45, so 75 degrees. So, T2 starting from t is equal to 0 will be obviously calculated by adding this T1 to 30 degrees. So, 45 plus 30 is 75 by 316, that is how your time T2 turns out to be. Capital T of course is 1 over 3 rho. Now, why am I calculating these two times is because the coefficients which are now required to be evaluated are given by these expressions 2 over t integral f t cos n omega t dt, that those expressions you have already learnt. Now, f of t is how much? What will be the, I mean these are the standard expressions, assuming that the function f of t acts from 0 to capital T, right. For example, if I have an excitation function which is going to be like this, and if this is the total time period, I will have to integrate from here to here, full time duration. But in my case, where what you see here is that the function f of t is non-zero only between time t1 and t2, it is only non-zero here, and the value of that f of t is actually constant p. That is the strength of that impulse or the force which is acting. So, that basically would mean that I will have to rewrite this as 2 over Now, that capital T is going to be 1 over 3 rho, and the integration will begin from T1 to T2, and then f of t will be simply p, because that is the constant value, and then cos n omega t, where I will replace omega using this expression, because in my case omega is going to be 2 pi over 1 over 3 rho. Okay. So all of these substitutions I will make, and that will give me this expression. You can work this out yourself, and of course, I have not replaced now. I mean, I will have to replace T1 and T2, which I have already got from this expression, which turns out to be 1 over 8 rho and 5 by 24 rho, right, where rho is, please keep that in mind, this is cycles per second or rotations per second of the blade. Is this clear? An, how the coefficient is actually to be evaluated. Please understand that for us to implement solution process by individually using the component harmonics of this periodic time function of the force, I will have to quantify what is An and what is Bn, and of course, what is A naught. A naught may not be so important from the vibration viewpoint, because that is going to be a static, constant DC or a constant force which will act. It is not going to fluctuate, it is not going to, it is just for a simple single degree of freedom system, it is just like a weight acting to generate a static shift. Okay. So, for us most important component obviously are An and Bn. Okay. So, out of which An is now formulated, at least in terms of the integral. If you evaluate this integral, which is very straightforward in this case, only one time function is involved, you can show that it turns out to be this. Try it out yourself, simple integration will give you this expression. Okay. If you want to find out Bn, it is quite again similar to An, and you can substitute all of these values to finally observe that the expression Bn that you have here generates Bn equal to 0. That means, irrespective of all your n values, the coefficient Bn is 0. Okay. Now, once these coefficients are obtained, I can substitute them back into this equation. Now, cos n pi will flip from -1 to 1 depending upon the value of n. So, that is how it is mathematically written as -1 to the power n to take care of the cos function, and rest of the expression look like this. Please make a note here that you can also write this f of t as An cos n omega naught or omega t minus phi n. You remember this? An would be square root of An square plus Bn square. This is discussed in a few slides back, and then there will be phase tan inverse of Bn over An, right. So, because in this particular case Bn is 0, you have An same as capital An as small an, and that is how it appears here in this part of the equation, but you notice that it is to be multiplied with this cosine function. So, that cosine function is appearing here, phi n here is 0 also. Okay. So, this is how for a typical excitation function which is not harmonic but periodic, you get to represent that periodic function as a series of sinusoids. So, if you simplify this f of t is appearing like a summation of some amplitude times cosine omega t of course multiplied by n, or omega n which should not be, or omega I must write. So, that I is changing from 1 to infinity. So, some amplitude and its harmonic time function I starting from let us say 0 to infinity. If I is 0, cosine function will be 1, and then as you keep on increasing the value of I, it is essentially series of harmonic forcing function. So, that is what we have done, that through Fourier series decomposition we have converted a periodic waveform or a periodic excitation function to its component sinusoids or harmonic functions of time. Okay. And then we treat, as we discussed earlier, we treat individual harmonic excitation functions as the only one which is acting or exciting the vibratory system, find out its response to that harmonic time function, then keep on finding it for other time functions, and then simply add them up to generate the total response. That is the whole philosophy which you have already understood. So, the job here was take an example like this, a practical example, and look at how its decomposition can be obtained, and then once you have this mathematical expression, you can quickly code this, you can quickly code this and then set the values of p or time t1, t2, and then you will get all the coefficients, and then your response is also straightforward to get. Okay, now a bit of an interesting analysis of these expressions that we have got. So, what we know is this a n was obtained like this, b n was 0, and then our f of t has been shown to be this, and a n and phi n are given by these expressions. You must note that ultimately it turns out to be a cosine function. Okay. So, it is a cosine function with some amplitude, that amplitude is dependent on value of n. So, all these, so in this plot which I am showing you, I am displaying the first 10 coefficients, that means I am displaying here a1, a2, a3, a10. Mathematically this series is an infinite series. So, you can keep on adding hundreds or thousands of these functions, but what you see here is that I have displayed first 10 terms or first 10 coefficients, okay, with of course this multiplying cosine function. What you notice, this is the 0th function, that is a naught, does not change because it is not multiplied by any harmonic time function, it is a constant value, that is what you have, p by 2, that is half. Okay. For the entire period of repetition I am plotting all these coefficients. What is the first harmonic time function? That is going to be cos n equal to 1. So, cos omega t minus 0, and a n will have its own value which is given by this. Okay. Cos pi is going to be minus 1, and because cos pi I is minus 1, you see that it is starting from negative value. Sin n pi by 4 will make it have some value which is not 1 or 0. So, it starts like this, and you can see that it completes one cycle, this is very important. So, the first harmonic time function in the period of repetition completes one full cycle. What happens for the second component or second harmonic 2, n equal to 2, a2 will have its own, will have its value starting from here, that is its amplitude, cosine function again, but positive, and then you see that there are 2 cycles getting completed in the same time period. Okay. This is your n equal to 2, it completes this one cycle and then 2 cycles. We expect that to happen. Second harmonic will have a frequency twice the fundamental frequency. So, you will expect in the same time period 2 cycles repeating, and then you can keep on watching other harmonic functions, n equal to 3, and then n equal to 4 here, which one is the black. Okay. So, you can simply see how their amplitudes are reducing. So, if I plot the frequency spectrum, you will realize the amplitudes actually, most of the periodic signals they monotonically keep reducing in their amplitude value. Frequency increases, the amplitude decreases. Most of the times, it is not 100% the case, in all the cases, but whenever the excitation time function is distorted from its harmonic form, let us say instead of this, if it is like this, right, all your subsequent amplitudes will keep on reducing monotonically, that is for sure. It is only in some cases where there are abrupt variations in the amplitude, there will be some interesting things, or they will be I mean this is not exactly guaranteed, in some case. So, it so happens that the amplitude first will reduce and then there will be some increase, and then, but then these amplitudes are still going to be smaller than the fundamental, that is for sure. Okay, let us see what happens, that if I now recreate the original signal by using the first 5 terms of the series. Okay, this was my excitation function, didn't I? I had this as my excitation function, my time period was this. Now, I have decomposed this into a series of harmonic time functions, and then if I keep on generating this, so let us say n is equal to 1 to infinity, instead of infinity, if I take only 5 terms and then add them up and recreate the original signal, this is what I do get. So, instead of a perfect step function like this, I get a slightly rounded function, but still you can say that okay, this is approximately recreating the original signal, approximately. There will be of course some errors associated with the recreation, and this is something which is going to happen for abruptly changing signals or abruptly changing functions, because it is very difficult for few terms to take care of such a sudden changes in their amplitude values. Okay, if I consider next add additional 5 terms, that means now I am trying to recreate this by considering the first 10 terms. Now, you can see that it is coming closer and closer to the original time function, and of course, there are some other issues where such kind of functions will still have problems at these corner points, and then it may not be able to theoretically recreate the exact step function. So, all of that accounted for, but fortunately for us most of the times the function is a smooth function, although it is not harmonic, it is still smoothly varying. Okay, most of the times I am saying that it is not always the case, but you will find that if it changes like this, then the chances are that only first few terms would recreate the original this function with much better accuracy. Okay. So, you do not need infinite terms in your decomposition to recreate original signal. In fact, later on the higher harmonic components are so small in amplitude that they can be easily ignored. Okay. So, therefore, coming back to the question of how you can evaluate the response given the fact that the Fourier series tells you that it is the decomposition into infinite terms, right. So, mathematically n goes from let us say 0 to infinity or 1 to infinity, but it is only mathematically it is going to that infinity value, but in practical purposes it suffices to focus or check only first maybe 3 to 5 to 7 or 8 maximums 5 to 6 terms, and with those terms included your response estimation becomes practically viable or easier to get, because otherwise you will keep on making so many computation for a given response. That is not required, because you can simply ignore higher harmonics, their amplitudes are generally going to be small enough to be ignored, particularly for excitation time functions which are reasonably smooth, which will be in most of the cases. Now, this is an example where one of the nozzle is shut off, that means this nozzle does not let the fluid in, and I basically close this nozzle, okay, this or this, whichever. If I am going this way, this nozzle is in. So, the fluid is going in, but the fluid is not getting admitted. So, then what is the period of repetition here? Will it be 1/3 of the rotation? So, now you can see that if you continue this, these two nozzles and this nozzle missing and so on. So, what is the period of repetition? Period of repetition will be 1 full revolution. This pattern repeats itself. So, your time period is not 1/3 of the rotation time, but it is going to be equal to 1 rotation, time for 1 rotation. So, now your time period of repetition will have to be recalibrated, and that value is 1 over rho time, 1 over rho s seconds. And with that substitution, and then of course, when you want to integrate it for this period, your integration will involve this integration and this integration, right, and that is why you are seeing there are two terms in the expression for A n and of course, for B n as well. So, in this particular case, please make a note that your A n is non-zero, but your B n is also non-zero. Okay. This all these expressions are quite same as, I mean, similar in the previous case. So, I leave it to you to evaluate it and get this expression, but the point is, in this case the coefficients A n and B n are non-zero, and that has an interesting influence in the sense that your terms are really not going to begin from or they are not going to follow cosine or nor sine function, right, because they will have some non-zero phase. So, you can notice here that the first harmonic function, of course, this is also interesting that your DC or a constant value A naught, okay, for the same amplitude of your step function of P. In the previous case it was P by 2, now it has dropped to 0.33, this P by 3, I guess, right. So, this is expected because in earlier case it was this signal, but now you have these two signals to cater to, and then the third one missing, which means that the effect of the missing inputs step function there would bring down the DC or the constant part of the harmonic decomposition to a lower value. So, that is why you see a drop in the static part of the series, and then look at the first time function here, okay, that is for n equal to 1. Can you notice here that it is starting here and it is not starting with an angle equal to 0. It is not a cosine function starting from unit value, either minus or plus, and this is because the value of phi in this case is non-zero, it is neither 0 nor 90. So, it is because you have both Bn and An being non-zero values, okay. So, there will be some phase which is going to start your sine function cosine function from here, and but then you can see that it completes one cycle, right? You can just follow it, this completes one cycle. The second harmonic function, the second term here is this one, and it completes 2 cycles. You can see that it is going to complete one cycle somewhere here and another one subsequently. Again here it is neither it is not starting from here, it is starting from here, okay, and so on. If we now take 5 terms, okay, it recreates the signal like this. Obviously, this does not really look like 2 rectangular pulses one after the other with the third one missing. So, it is all because whenever you have abruptness and some the missing pulse itself will be like an generating some amount of abruptness there is no consistency. Okay. Once that is lost, you need even more number of terms to recreate that. Okay. But because ultimately you are just adding more of such terms and their summation should reach out to the original signal. So, therefore, you see that in the earlier cases at least you came reasonably close to your single impulse, but in this particular case the signal is not really up to the mark. Now, if I add another 5 terms and make it 10, now it starts coming to 2 pulses, rectangular pulses one after the other. So, 10 terms bring it reasonably close and then you get closer now by taking 20 terms. So, now you need double the original terms to have some kind of a reasonable recreation, but at the edges you can start seeing some ripples being generated. Those are typical of such kind of an abrupt time functions. Okay. So, are you clear about now how a periodic excitation function are actually decomposed into component harmonics using Fourier series decomposition? A small point there to make here is that this particular integration function which we use, it is imperative for us to somehow get this f of t written in mathematical terms, then only you will be able to integrate it, right. But suppose, as we are going to see in the next example, that if the function is something which cannot be captured mathematically, how do you capture this entire thing in mathematical expression, neither sine nor cosine, log or exponential and something like that. If you have a blast excitation function maybe like this, you may be able to capture that mathematically, the way we have seen in the Duhamel's integral case as well. So, maybe some exponential term and some this linear term, but if the function is like this, then we are usually left with no other option but to do this integration numerically. Okay. So, you discretize this and then after discretization you can get this f of t written in terms of some discrete values or a series of discrete values, and instead of integration then you can sum them up and so on, right. So, this is numerical way, alternative numerical alternative to calculating this mathematically. Okay. That is just a small input that is required here. So, this is the summary of this lecture. We discussed today how exactly the response to any periodic excitation forcing function is obtained. In that context, we discussed couple of examples. What we also saw that typically as long as the periodic excitation is not abruptly changing, only a few first harmonic terms in the Fourier series is good enough to get a reasonably accurate response. So, this is the recall question for today's lecture. So, what you have been given is a simple vibratory system, single degree of freedom system with a forcing function, as you can notice is not a simple harmonic excitation function, but a function comprising 2 different frequencies making up a total periodic excitation force. The stiffness and natural frequencies are given. You are supposed to get an expression or simply write the expression for steady state vibration response as a function of time, of course, ignoring damping. So, it is an undamped case. So, how would you write it? You can see that the forcing function had 2 components. The first component has an amplitude equal to 3 Newton and the frequency of 20. So, this represents the response to the first harmonic term and this represents the response to the second harmonic term, and that simply added up assuming linear vibratory system is the total response as a function of time. As a general case, particularly when you have damping in the system, it is essential to consider the phase angle, which is ignored here because it is an undamped case. and that actually gets automatically taken care of anyways in the denominator, because the denominator in this case is going to be negative. But as a general expression, you will have to write the response cos omega t or omega 1 omega 2 t minus phi. The only difference now here would be, as a general expression, it has to be f by k upon square root of 1 minus r square whole square plus 2 zeta r whole square into cos omega, let us say I t minus phi I, right. Now, here also this r is actually based on which particular harmonic you are considering, and therefore, the value of r here, that is omega over omega n, is actually 20 over 10, whereas in this case the second term you can see that this value of r is 40 over 10. So, omega here is 40 radians per second, whereas here it is 20 radians per second. Just have a look at how your excitation function is, and therefore, for each of the harmonic excitation time function, you have to appropriately take the value of r. That is the most important part in this particular example that you should understand. Okay. Each phase angle again will have to be calculated based on the value of r for this time function that you are accounting for. Okay. So, that is how it will have to be calculated.